or stuff you're confused about, or whatever else. My favorite color. You know.
What is your favorite color?
Purple. Yeah.
That's a good color.
Yeah, Giselle.
Do you do number 23 on the problem set?
Sure.
Not one of them?
Girl, I want all. Yeah, I know this one. You're good. I'm asking one.
All right. 23 says from the top. Hey. Shh. Thank you. Little hoarse, so I don't want to have to it hurts to talk, Work with me a little bit. From the top of a 100-foot building, Ellie observes a car moving towards her. If the angle of depression changes from 17 degrees to 37 or 31 degrees, how far has the car traveled? So what we're looking for is this distance x, right? Everybody cool with that? Okay. So my angle of depression, I note this is the same as 17 degrees, and this one is the same as 31 degrees. So far, so good. So far, so good, Giselle?
Yeah.
Actually, I mislabeled this. This isn't x. X is how far the car has traveled. That's x. So I'm going to call this piece y. So this side should be x plus y. Is that okay? Sorry. Is that a car alarm going off? Hear that rhythmic beeping?
No.
It's awful annoying. All right. So again, we can assume that this is a right angle here. So for this right triangle, I can say that tangent of 31 is equal to 100 over y. I can solve that directly, right? And for the other one, the other right triangle, I can say that tan of 17 is equal to 100 over x plus y. So from here, I can say that y equals 100 divided by tan 31. So this is going to equal 100 over x plus 100 over tan 31. So to solve for x, I can multiply both sides by that denominator. I'll divide both sides by tan 17. And then subtract the 100 over tan 31 from both sides. And that should be good. Let's check that out. First stop, got to make sure my calculator is in degree mode. And then I'll do 100 divided by tan 17 minus 100 divided by tan 31. And I get about 160.7 feet. Does that match up with what the answer is supposed to be, Giselle? Do you remember?
I'm not sure.
It's an odd. Yup, 160.66, so good enough for us. Does that work out okay for you?
Yeah, can I just get a second?
Yeah, you take all the seconds you want. Not all of them. Take several of them, though. More than one. You can have 2 or 3. These are supposed to be jokes. Where she said, can I get a second? Done. Okay. Yeah, you're welcome. Happy to do it. Sophia. 22? Okay. Says Manuel is going hiking with his GPS device. The marker at the trailhead says his current elevation is 174 meters above sea level. The next marker he passes says he is now 210 meters above sea level. The eraser part of my pen has stopped working and it's super annoying. That's what I'm dealing with today. And his GPS says that he has gone a horizontal distance of 1 kilometer. What is the average angle of incline for Manuel's hike? So what I'm going to be interested in is this triangle here. And we're interested in that angle. So far, so good, Giselle? Nope, this is Sophia's question. My apologies. Still a question behind. So what is this side length over here? Gotta be. The one with the arrow next to it. Excellent. So 36 meters, right? What is the base of that triangle gotta be? Not 1 kilometer, but am I going to write it as 1 kilometer? I'm going to write it as 1,000 meters. Why do I need to do that? Yeah, because the other unit is in meters. Got to have matching units. Either they both have to be kilometers, they both have to be meters. And then I'm done, right? So theta should be tan inverse of opposite over adjacent. And it's calculator time, homie. Tan inverse 36 divided by 1,000 is 2.06 degrees. How'd you like that? No big deal, right?
Hardly thinking about the picture.
Yeah. Getting the picture and it's like, oh, okay. That's I can do that. Decoding the reading comprehension side is the tough part, right?
How come it's an inverse?
Because we're looking for an angle measure, right? The inverses give out angle measures. The regular versions take an angle measure and output a number. So as soon as it's asking for an angle, I know I'm going to be using an inverse. Is that cool?
Yeah.
Good questions. Anybody else? Well, that hurt to say.
Is there calculus supposed to be in like degrees for all these questions?
Well, I mean, I guess this one doesn't say expressly like what unit your angle should be in, but like nobody gives radian measures for like real world stuff. You know what I mean? Like if I asked you, hey, what angle is that ramp at out on the construction site? And you tell me 0.47 radians, I'm going to slap you in the back of the head and be like, what? You know what I mean? Like, it's not like in the real world, we just really don't do that. Rita. Sure. You guys are big on the story problems today. A guy wire I think that's probably supposed to be connects the top of his telephone pole to the ground for added stability. Well, that was kind of it. If the pole is 27 feet high and the wire is 30 feet long, what will the measure of the angle formed by the wire and the ground be? So there's our picture. So relative to that angle, I have opposite and hypotenuse, so I'm going to be using sine inverse. And that'd be it. Again, we're looking for an angle, so we're going to definitely be using the the inverse version of whatever. And we get 64.2-ish. Oops a daisy. But no big deal, right?
Yeah.
Who's next? Ugh. By the end of the day, my voice is just shot right now. I don't even really feel sick. Well, I felt sick this morning. But I feel fine now, but my voice has gotten considerably worse as the day's gone on. A little froggy. Ribbit. Okay. Well, if nobody's got anything else, let's move on to the next section. This is the last section in chapter 3. So one of the, in section 4.3, we're going to look at some more applications of trig functions. And one of the big applications we have for trig functions is with navigation. When we're describing navigations, what the industry standard is to use a course or a bearing to represent our angle. So in a course for a course or a bearing, the angle that we're describing starts at due north and rotates. Just have to make sure I'm getting this right. Clockwise. Course and bearing angles are only defined from 0 to 360. There's no negative bearings or courses. They're always going the same direction. There's no we spin around more than one time courses or bearings where there's no angles bigger than 360. But the key that you have to remember is starting at north and we're going clockwise. Okay? So let's just practice for a minute. So let's take these bearings and convert them into standard position angles. So for 58 degrees, again, we're starting here at due north, and we're rotating clockwise. What quadrant am I going to end up in? In the first quadrant, right? Because I know there's 90 degrees in a quadrant. Everybody's cool with the bearing that I've drawn here? Now, if I want a standard position angle, where does my standard position angle begin? The positive x-axis. And which way do I rotate for a positive angle? Counterclockwise. So that would be my standard position angle. What does that standard position angle have to be here? 32 degrees. Great. How did you get that? 90 minus 58. Everybody happy with what we did there? Okay. Yes. Sure. Let's do the next one. So 164. What quadrant are we going to end up in with our bearing of 164? Quadrant 4, right? So we're 90 degrees to here, and then 74 more will get us to here. Everybody agree with that? So now let's draw our standard position angle. We start on the positive x-axis and go counterclockwise. So that's what we're doing. So there's 90 degrees for that quadrant, 90 degrees for that quadrant, 90 degrees for that quadrant, and then how much for this piece? 90 minus 74, which is 16. So my theta should equal 90 plus 90 plus 90 plus 16. So 288. Everybody so far so good? No big deal so far, right? Let's do a couple more just to make sure we got it, because we will not be able to do this successfully if we can't do this basic skill. The next one is 221. What quadrant am I going to end up with a bearing of 221? Quadrant 3. So we're 90, 180, and then 41 more. Will give us 221 total. Everybody agree with that? And then our standard position angle, we start on the positive x-axis. I do 90, 90, and then how much more? And 90 minus 41 is 49. So my standard position angle then is 90 plus 49, or 229. So look good so far? Our last example is 299. What quadrant is that going to be in? 2. So 90, 180, 270, and then like 29 more. Everybody's cool with how I'm doing this? Pretty easy, right? So standard position angle is here, where we've gone 90, and then 90 minus 29, or 61 degrees. So theta is 90 plus 61, which is 151. Is everybody okay there? Okay. All right. Let's take a look at an example problem where we have some bearings. An example of one of these navigation problems. That was not how I expected that to get copied and pasted in. Okay, so this says a boat leaves a port and averages, I should probably say averages, 40 knots. That is, 40 knots is nautical miles per hour, traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels at 55 knots for 3 hours. What is the distance and bearing of the boat relative to its starting position at the port? So I hear that I have 2 legs of my journey, right? I'm going 40 knots for 2 hours, and my bearing is 215. And then I go 55 knots for 3 hours, and my bearing is 215. Okay. How far did I go on that first trip? Carmen?
I just want to say, for the second one, shouldn't it be,
Oh, 162. Thank you. Yes. Perfect. Yes. 100%. Thank you. If I make a mistake, catch them early like that. It makes everything much easier than having to go back and erase 100 things afterwards. 80, right? Is the answer for how far did we go on that first leg of our journey. Since knots are nautical miles per hour, I'm just going to do that rate times time to get a distance. So 80 nautical miles. How far do we go on the second leg of our journey? 165 nautical miles, right? 55 times 3. Everybody's cool with that? Okay, so we're just 245 nautical miles from our starting position, right? Nope. The boat traveled 245 nautical miles, but imagine if you are starting here, you walk like 3 blocks this way, and you walk 5 blocks this way. You're not 8 blocks from home. You're that far from home, right? Which is not 8. Well, I picked bad numbers. Let's make this one 4. And then this is 5, right? You're 5 blocks from home. Or 5 units from home, or whatever the unit is there, right? So it's not going to just be like, oh, okay, that's the distance. So let's draw a picture of kind of what's going on then, right? So I'll try to draw a big picture so it's easy to kind of write in and describe what we're doing and how we're doing it. All right. So leg 1, I'm going to color in red, and leg 2, we're going to color in blue. Everybody's cool with that? So the first thing I'm going to do is I'm going to draw in my 215 degree angle. What quadrant will that 215 degree bearing land in? The third quadrant, right? 90, 180, and then 35 more. Everybody's cool with that? So what is my standard position angle going to be? 90, 90, and then 55. So 235. Everybody good with that? And let's say that this length here is 80 nautical miles. That's all for leg 1. Oh, I don't know why I shouldn't have used blue there, huh? Yep, that's good on you. Yeah, let's change that to green or something, huh? Thank you. And I'll put an SP next to that 235 to remind us that that's the standard position angle then. Everybody cool now? So currently our boat or whatever would be here. Everybody agree? So what I'm going to do now, actually let me do this. Draw it there. So I'm going to draw another XY axis. And I'm going to draw my next leg of my journey, which is 162 degree bearing. Which quadrant does that put me in? Quadrant 4. So we're like starting here. We do 90 and then like 72 more. But again, I want to convert that to a standard position angle. So that's going to be 90, 90, 90, and then 18, so 288. Go back and look at my picture here. Is everybody okay with what I've drawn here? So what we're looking for then is this length and that angle. Everybody's okay with that? So we're looking for the length of that silver and the angle that that silver piece forms. So they drew it up here in silver,
Oh.
right? Is that okay? Everybody agree this is what's going on, right? There's a nice, accurate picture, a descriptive picture of what's happening. The only thing I didn't do a very good job of is probably scaling how long the blue and red pieces were, but like we get the idea. So how the heck, so what our goal is going to be, what I want is I really want to find that X and Y. If I know where that X and Y is, I can use the Pythagorean theorem or the distance formula to figure out the length of that silver piece. Everybody agree with that? And if I know that X and Y, I can figure out an inverse function to get me the angle that I'll need to figure out theta. Everybody agree with that? Okay. So this is the way I'm going to think about it. Is this to get to this location over here that I'll call x1, y1, what I'm going to be doing is I'm going to be going over this much and then down this much, right? That'll be the same as x1, y1. Everybody agree with that? And then to get to that silver xy, from x1, y1, I'm going to be going over this much and then down this much. Everybody agree with that? So this then xy would really be like x1 plus x2, y1 plus y2, where this is like x1, that's like y1, this is like x2, and that's like y2. Everybody okay there? All right. So what this boils down to is I need to figure out how to find x1, x2, y1, y2. Does that feel okay? So let's look at x1 and y1. What do you notice about that, x1, y1? I have a right triangle here. Everybody agree? Do I know the hypotenuse of that right triangle?
Yes.
Yes. Do I know the angle that that triangle forms with the x-axis? Yes. Should I be able to solve for the other side lengths if I have a right triangle and I know an angle and a side length?
Yes.
Yes. What do I have to be careful about if I'm taking that approach? What quadrant is this in? We're in quadrant 3, so the x and y side should be negative. Now, I can remember to do that, or instead, I can use my standard position angle with sine or cosine or whatever, and it'll just take care of the signs for me. That's what I would recommend. Okay? Yes. Sure. So, x1, if I'm solving for this, I would write like cosine of theta equals adjacent over hypotenuse. Correct? Everybody agree? Or if I solve for x1, I'd get that. Well, look at the picture. x1 is adjacent, right? The angle we know is like here, the 55. So x1 is the adjacent side, and the 80 is the hypotenuse. So that's why I'm using cosine. Because if I use theta instead of the 55, I don't have to remember to make that negative since it's lying in the third quadrant. Because remember what we're finding is this point. That point, the x value is negative because it's in the third quadrant. If I use, though, instead of 55, if I use 235, I don't have to remember to make my answer negative afterwards, which is what I'd prefer to do because, like, it's pretty easy just to forget. So that should be negative 45.89. What's y1 going to be? Maybe I'll write that, how we did that in there. Yep, that was our standard position angle. How am I going to find y1 then? No, I didn't have to make anything negative. The calculator took care of that for me. I'm going to use sine. Now, how am I going to remember that? Actually, these don't have any units. On the unit circle, cosine is x. To solve for an x, I'm going to use cosine. On the unit circle, sine is y. To solve for a y, I'm going to use sine. Right? No big deal. Easy to remember. Everybody agree? That's nice, Mr. Kulik. I like it when there's like synergy there and things make some intuitive sense. You like when people use synergy in class too? That's a fun word to say. So I have negative 65.53. Do I really need to work to write out how I'm doing x2? Isn't it going to be like exactly the same thing? You got it. Was that like 165 and then cosine of 288? And 165 sine 288. Bless you, bless you. So I have 50.99 and then $156.92. Negative 156.92. Everybody's cool with how I came up with these numbers? Okay. So I tried to color code the x's in yellow and the y's in green. Does that feel okay? I know it's a lot. Here's the lovely part, though. Is drawing the picture, do I really need this for anything? If I'm doing another one of these? No, not if I made this observation already. Because I don't need the picture to get x1, x2, y1, or y2. Right? What do I need from that? I just need the length of the trip and the standard position angle formed by the bearing. I don't need the picture, that complicated picture that I drew to get either of those two things, do I? Bugs flying around in here. All right, let's see. We got x1 plus x2 and then y1 plus y2. So that's negative or 510 comma negative 222.46. Everybody's cool with that? So to find that total distance then to that point, I could use the distance formula. Well, what is the other point I'm using? The origin. So this really just works out to like just the square root of x squared plus y squared, right? Since the other point is 0, x minus 0 is x. And then y minus 0 is y. Well, that's awful nice. So I get 221.51 for my total distance, which makes sense, right? Is that 221 or 222? I forget now. 222.51. And this would be nautical miles is my unit. No. I thought we'd have done more yesterday. We didn't. That's okay.
Will we have Wednesday?
Huh?
Will we have Wednesday?
I don't know yet. We'll see how tomorrow goes. You know, I'm not in a massive rush. Just like a regular rush. Wednesday would be the earliest possible test date. Let's put it that way. Okay. Talika. Yes. All right. We still have one more thing to do, though, right? Was it asked? What does the question ask for? So we have the distance. We did that. Still need that bearing, though. Wait. Okay. Okay. Here's the good news. The hard stuff, already done. So what I'm going to do is I'm going to plot that point xy. So it's like down here somewhere, right? 5 over and 222 down. Everybody agree there? So to get my bearing, I want that angle. Everybody agree? That angle is going to be 90 degrees plus this spot. I'm going to call that spot phi because it's the angle formed between a terminal side and the x-axis. So what is my bearing going to be? And how do I calculate phi in this case? Tan inverse of the absolute value of y over x. Well, that's not bad, right? This was so fast compared to like the setup for this. And really, what was the longest piece of the setup? Drawing the stupid picture that I've just illustrated to you that we don't really need to draw every time, but like the first time we definitely needed to draw it because, you know, nobody would have believed me had I just told them what to do. Where's that? Oh, there it was, abs. I'm just going to use the absolute value here because I'm just stealing the numbers. Math, and then it's number and ABS. So I get 178.69. And I'm done now. Let's do another one. We'll do it the streamlined version. We're not going to draw the big complicated picture to verify to you what was going on. Okay. All right. The next one says a plane can travel 525 miles per hour under its own power. If a pilot flies at the plane's maximum speed on a bearing of 125 degrees, and there's a 35 mile per hour wind traveling at a 200 degree bearing, what is the plane's actual speed and bearing? So what are we looking for here at the end? Speed and bearing. Notice that here I'm asking for speed rather than distance. Everybody note that? Does that make much of a difference to us? No. So there's really two things happening here, right? I'll call these guys forces. So we'll call this force 1 is going to be the plane. So the speed there for the plane is 525, and the bearing is 125. Do we want a bearing though? No, thank you. What do we want instead? Standard position angle. So that bearing is going to be down here in quadrant 4, 90 degrees, and then 35 degrees. So my standard position angle is going to be 90 plus 90 plus 90 plus 55, which is 325. Everybody's cool with that? force 2, which is the wind, what's the speed here? 35 miles per hour. And the bearing is 200 degrees. But do we want a bearing? No, thank you. What do we want? Yeah, we want a standard position angle. So a 200 degree bearing will be in quadrant 3, 90, 90, and then 20 more. So my standard position angle is going to be 90, 90, and then 70 more. So that's 250. And I'm going to go back here and maybe just do this. Is everybody okay there? Okay. So my total, let's do this first. So I'm going to compute an x1 and y1 for this force. That's just going to be the speed times cosine of the standard position angle. And then speed times sine of the standard position angle. And we'll do the same thing over here. Everybody okay with what we're doing? Do you need me to get out of here, bugs? Do you need me to pause? Okay, just tell me to wait up then a second. It's okay. Notice that I'm not going to bother with the big crazy picture here because we don't need it to justify why we just need to add the coordinates, right? That's really the only reason I drew the picture, was to justify really what I'm doing is just getting the coordinates for each of these and adding them together. So I'll just go to my calculator. So 418 for the first, for the x component. And negative 334 for the y component. Does that feel okay to everybody? Okay, so that's the total position. What's the total? How do I find the total speed? Just use the distance formula with the origin and that total position. So 535.13. And this would be miles per hour. The last thing I need is the bearing. So to get that, I'm going to start by plotting that total position. So that total position was 400 to the right, and then like 300 down. So somewhere down here in the fourth quadrant. So the bearing from north is going to be 90 plus that angle formed between the terminal side and the x-axis. And remember, the way we calculate that angle between the terminal side and the x-axis is with tan inverse of the absolute value of y over x. And that's going to just be a calculator problem. So 128.62. Did you do 90 plus tan inverse of the absolute value of y over x?
Oh, I did absolute value.
Yeah.
Like that.
You got to have that absolute value in there if you're doing an angle, if we're doing something like this. So again, when you're finding that total angle with the inverses, it's always going to be adding that phi or whatever. So you need to use the absolute value anytime you're doing a phi there.
How do you use that absolute value?
Well, you know, I mean, like I use the absolute value because I'm like being a jerk about all the decimal points and making sure I can make this as accurate as possible. But it's under the math menu and then the number option. You should see ABS. That's the absolute value command. You're welcome, Ava.
Can you check this?
Not really. I mean, it's like, it'd be like just going and checking the basic parts of the work. Like, the problem is that, like, I could check if this actually satisfies the Pythagorean theorem there.
Yeah.
But, like, if I screwed up one of these numbers, I'm still gonna, it should check out right. You know, like there's so many places to kind of make like a silly mistake.
Yeah.
It makes it kind of tough to check. I'll tell you the place where most often the mistake gets made, and it's a dumb one, is that students plot their point wrong, and they get it in the wrong quadrant, and end up drawing the wrong picture, so the angle phi, or their angle theta, their bearing is wrong, because they drew their picture wrong, so they added the wrong stuff. To be honest with you, that's the most common mistake I see students make.
Okay.
Which is like,
Yeah.
what are you going to do with that?
Yeah.
Like, you know, like you misplot a point, that's a hard one to catch if you've done it the first time because you just don't check it.
Great. Okay. Thank you.
Yeah, I wish I had a better answer for you, but it's one of those where it's just kind of like, you could sketch out the picture and see if your answer looks reasonable. Like the drawing we did before, if you like were very careful about how you drew things, it would look like it's in the right spot. Like the coordinate should be in about the right spot.
Okay.
But like, that's probably the best you can really do as a checker.
Okay. Thank you.
You're welcome. Rita?
Can you go over like what you put into your calculator when you're finding out that you do like exponent y? I was like getting like different numbers than what you got.
What mode is your calculator in?
Degree.
Okay.
Like, what-
So I didn't calculate either one of these. I just did x1 plus x2 and then got that number.
Oh, so you just like put into your calculator 525.
I did 525 cosine 325 plus 35 cosine 250 and just got the number. That's what I did, because I don't need the actual number for x1 and x2 separately. I just need their sum, so I'm not going to bother like writing both of those numbers down just to add it together again on my calculator. I'm just going to do it all in one line and just be done with it. You know what I mean?
Yeah.
Just going to save myself the hassle. And if you look at this, this was much less writing than the last problem, right? Where we streamlined things a little bit and we didn't draw the big scary picture. That was like, that's a pretty complicated picture you just drew, and like there's a lot of labeling going on there. It's like, look, I just did that to justify why I have to do x1 plus x2 and y1 plus y2 and why I get x1 and y1 that way, you know? But after I've justified that, it's like, really calculation-wise, what did I do? I found these. I did this. I really wrote that down. I didn't even calculate any of those things. This was the only thing I calculated. You know? And it was all the calculator did all the heavy lifting for me. I just had to kind of set it up. Is that okay?
Yeah.
Of course. That's it for section 3. It's just this one kind of skill. You guys should now be able to do. Yeah. And then that's got to be the 6th or something, I think. So let's plan on this then for the next class. We'll spend some time in class letting you guys kind of work on some of these navigation problems, these navigation story problems. Maybe at the end we'll give you guys like a partner homework quiz based on it after you've had like an hour or so in class to kind of work together on some stuff and ask some questions. We'll see what Mr. Kulik has in store for you. That maybe happens or might not. The following class would be the review day, and then we'll do the test. What, for you guys, that'd be Friday next week? Does that sound reasonable? So you get like a full day to just kind of work on getting better at this skill. If you did not great on the homework quiz, probably go back and take a second look at the worksheet 1 and 2 stuff. We can still deal with questions and stuff on that also. But that's a pretty important skill to get good at. Just FYI that if you're like, I did a lot worse than I expected. If you want to come back during community time, I can show you let you look at your paper and we can talk about what you did or didn't do. I mean, you could do it now, I guess. I was just still kind of talking. When you say now, I mean like in a few minutes. But I'll get those back to you guys as soon as everybody's taken them, kind of thing. But you know how that goes. Some of us are feet draggers when it comes to making stuff up, and some of us are really good. But, you know, 1 foot dragger is all it takes. You know what I mean? All right. I'm done talking now. Is that okay? Sure.